Hello everyone and welcome to lecture. In today's lecture, one of the things that I want to be describing and talking about is how to find the area bounded by a polar curve. So a curve in polar coordinates. And this is going to be similar to our Riemann Sum procedure for the arc length discussed last lecture. We're going to consider a polar curve, which you'll remember is just a parametric curve where the radius is a function of the angle theta. So the curve is just parameterized by theta. In general, maybe it looks something like this, where we have the endpoint on the curve, the beginning point on the curve right here, so this point right here is at an angle, we'll say theta A, and the endpoint on the curve is at the angle theta B. And points on the curve are given by x of theta is equal to r of theta cosine of theta. Y of theta is equal to r of theta sine of theta for theta in the interval from theta b to theta a. And we want to kind of come up with an idea of approximating the area. Right? And it turns out that we can do this very, very nicely by, again, considering a partition starting at theta 0, theta 1, theta 2, and so on and so forth, all the way up to theta n minus 1, theta n. And you have to have these be strict inequalities. And if we consider the segment of a circle going out to a sample point in each one of these regions, so I'll just have a partition here with a couple different pieces in it. This is angle theta 1, theta naught. Theta naught is theta A, theta n is theta b. This is theta 2, theta 3, and theta 4. Which in this case is just the angle theta b. So if we want the area bounded by this curve, an approximation to this is going to be if we take a circular segment at some theta k in each one of these intervals of theta and find the area of that segment. So for instance, if I sample the radius here at this point theta k, this angle is theta k and the radius going out to this point is r of theta k. This segment, this circular segment, gives me an approximation to the area traced out by the function over this segment right here. And similarly, if I do this for each one of these segments, pick a sample point or sample angle and consider the segment formed, the circular segment formed by that sample angle, the sum of the area of each one of these segments is not the exact value of the area traced out by this polar curve, because you have regions where the circular segment goes over and regions where the circular segment doesn't capture the actual area, but it is an approximation to the total area. Right, so for, we'll say, the kth segment here, you can go through and say then that, well, what is the area going to be of this kth segment? We know that the area of a circle, of a full circle, is pi times r squared. So in order to quickly figure out the area of this segment, we can really just use some basic geometry. We have that this angular segment right here, I'm calling the K angular segment, and the difference in angle from the beginning to the end point of this segment is delta theta k. It's the distance between each one of these angles, theta k plus 1, or theta k minus 1. And the radius of the sampled angle in this interval is just r of theta k, whatever the radius function is of this sampled angle, or I'll call the sample angle theta k star, just so we don't get confused. So for a general circle, if I want the area of just a segment of the circle, well, I can look at the fact that the area, we'll call it delta AK, of this segment over the total area of the circle, pi times rk squared, that's the total area of the circle, has to match the ratio of angles, which is going to be delta theta k over 2 pi. Right, this is essentially saying that the angle of this segment, delta theta k, of radius rk, right, the area of this segment divided by the total area of the circle has to be equal to the angle of this segment divided by the angle around the entire circle. So what's nice about this is that the pi's cancel out, and we get an exact expression for the area of a segment here to be delta AK is going to be equal to RK squared over 2 times delta theta K. So this is the correct formula for an approximation of the area of one of these segments, each one of these segments, because RK is just R of theta K, which means that a sum that approximates the total area bounded by this curve is going to be the sum from K equals 1 to n of delta ak, the sum of each one of these segments, or Sn is equal to the sum from k equals 1 to n of r of theta k squared over 2 times delta theta k. And we expect that the exact area is going to be the limit of this as n goes to infinity, the limit of this Riemann sum as n goes to infinity, which exactly converges to the integral from theta a to theta b of r of theta squared over 2 d theta. So this is the area, the formula for the area bounded by a polar curve. And I want to make the point here that this sample angle can be any point theta k star between theta k minus 1 and theta k, just like normal Riemann sums. Obviously, if we choose a different scheme, you can pick, say, the right endpoint Riemann sum or the left endpoint, or really any point in between. But the convergence here is when we have convergence of the upper sums and the lower sums for this Riemann sum, we have that the integral exists, and it doesn't care about our sampling procedure, which is very cool. And so now the idea is that we want to kind of visualize this. And so what I want to do right now is show you a really good example of exactly what this process is doing, the Riemann sum process. So this is a picture of the spiral with r of theta equals theta. So the idea is that the angle theta is just kind of growing, or the radius is growing exactly linearly with the angle theta. It's getting bigger and bigger and bigger as theta gets bigger and bigger and bigger. For any angle, the radius outward is the angle that we measure from the x-axis. And this is an integral that we can go through and calculate very nicely, very relatively easily, using this formula. But what I want to do is show you, what's going on with the Riemann sum. So this is the picture of the circular sectors. Right, we have 3 circular sectors for 4 points in our partition. If I increase this to 5, we have 4 segments and 5 sample points. Increase it to 6, we have 5 segments, 1, 2, 3, 4, 5, and 6 sample points. In even for 6 sample points, the approximation is really bad. Right? You don't have much. There's a lot of extra kind of area here that we're not capturing. But rest assured, when we take this to a much larger value of n, like say 100, this area, right, the error area, the stuff that we're missing, is getting much, much smaller. And you can, I think, clearly see that this is going to 0 as n goes to infinity. So this is why the limit of the sum of the areas of each one of these circular sectors, as n goes to infinity, is converging to the true area trapped in this region. I think this is a really kind of very neat example to kind of go through and do. So let's go through and compute the area that's bounded by this polar curve. So for this example, we have that this is going to be the integral from just 0 to 2 pi. That was the curve that I just plotted. I'm going from theta equals 0 to theta equals 2 pi of r of theta squared over 2 d theta. So r of theta was equal to theta, and so this is the integral from 0 to 2 pi of theta squared over 2 d theta, which is going to be 1/2 theta cubed over 3 from 2 pi to 0, or 2 pi cubed over 6, which is 4 pi cubed over 3. And so this value, 4 pi cubed over 3, is exactly what the area of the region bounded by the spiral that I just showed you earlier is. So it's what the sum of the areas of each one of those bisectors is converging to when you get infinitely many cuts, which is the exact area bounded by this curve. So what I want to do is show this on another example that's a little bit more complicated, but not too much more complicated. And this is going to be the rows function that we talked about in class the other day and in the last lecture video. And I made the observation that when we have and recall that this rows curve is the parametric curve that is governed by the function r of theta is equal to cosine of n theta. And we're going to focus on just one petal of the rows itself. Remember that we made the observation in class the other day that when n is odd, there seems to be the same number of petals as the integer n. So cosine of 5 pi rows has 5 petals. Cosine of 3 pi has 3 petals. And if n is even, there's double the number of petals. So in this case, when n is 2, there are 4 petals. When n is 4, there are 8 petals. And when n is equal to, the highest here I went up to is 5, so I can just change that to 6. You get 12 petals. So if I want to figure out the area of one petal of the row, it's just one petal, we're seeing that it's very clearly symmetric. You can prove that it's symmetric due to the behavior of the cosine function and the angles for even values of n, and it has certain other symmetries as well even for odd values of n. So not for n equals 1, but for n equals 3, say, or n equals 5. It does have certain symmetries. So if we stick to, we'll say n equals 2 here, and apply our Riemann Sum procedure to one of the petals, then you can see very clearly that as n goes to infinity, right, the sum of these sectors is going to be in fact converting to the actual value of the rose petal. So the question here then is going to be, right, how do we evaluate this integral? And this is kind of a difficult question. The last example, right, we had the bounds for the spiral explicitly given to us. for this problem right here, right, we don't necessarily have bounds. We need to go through and figure out what the bounds are for one petal of this rose just using the function r, the radius function. So this isn't too difficult to do. We have that r of theta is equal to cosine of n theta for the rose. So the parametric equations are x is equal to cosine of n theta times cosine of theta, and y is equal to cosine of n theta times sine of theta. And what we want to do is compute the area of one petal. Now the thing is that we want to solve for the theta A that gives us the very beginning of a petal. So this first angle should be the angle that corresponds to the beginning of a petal. And the lower bound theta, or the upper bound theta B here, the lower bound is theta A, the upper bound theta B, this should correspond to the end of the petal. Okay, so the radius basically should be going to 0 at each one of these values, theta A and theta B, as the curve kind of stretches around. At the beginning it's at the origin, it loops around once, and then it comes back and ends at the origin again. So the key to this problem, doing it right, is to figure out exactly what the upper and lower bounds are for a given petal. And we know that from the formula we just showed, this is going to be r of theta squared over 2 d theta. Assuming we can choose these values, theta A and theta B, correctly for the petal. So basically, once we have these bounds, we can go through and do the integral, and you can even do the integral without the bounds if you want to. I think that makes a lot of sense. You just need to make sure that after you find the antiderivative, you go through and figure out what the exact bounds are. Right? So it's really, you can go through the process of finding the correct bounds before you integrate or after you integrate. You're going to have to do it eventually at some point. But I think it's easier to just do the integral first and then go through and find those bounds. It's just the integral of cosine of n theta squared over 2 d theta. You'll recall from your Calculus 2 class that cosine squared of any angle will always be equal to 1/2 1 plus cosine of 2 theta. Or 2 phi. And this is the best way of evaluating this integral right here, because this integral then will just be the integral from theta A to theta B of 1/2 1 plus cosine of 2 n phi is n theta here, so cosine squared of n theta will be 1/2 times 1 plus cosine of 2 times n theta over 2 d theta. which is going to be 1/4 times the antiderivative of this with respect to theta, which will be theta antiderivative of cosine is sine. This will be plus 1/2n times sine of 2n theta from theta b to theta a. And so this gives you the area of any segment, right, of this region, or of this rose curve. But like I said before, we are specifically interested in one petal, finding the area of one petal. So the picture that I drew here is the rose for n equals 2, but the integral that I've done here is the general integral for the rose. And this is what I want to also kind of lead with to show you how to do this in general for any one of these curves. So if the petal starts at 0, the radius is 0 at whatever angle this angle is right here, and then goes positive, and then goes back to 0, right? We can solve for this mathematically. It's basically all of the points where r of theta star is equal to 0. R of theta star is cosine of n theta star, and this equals 0 when n theta star is equal to plus or minus pi over 2 plus or minus 3 pi over 2 plus or minus 5 pi over 2, and so on and so forth. So that means that the theta stars that we're looking for are all of the points where plus or minus pi over 2n plus or minus 3 pi over 2n plus or minus 5 pi over 2n, and so on and so forth. And so what I want you to do is think about what we've done here. We've essentially gone through and solved for all of the values of theta for which cosine of n theta equals 0, which is all of the values of theta for which the radius is 0, or all of the values of theta for which the curve crosses the origin, because it has to loop back if r is 0. Whenever r is 0, it has to cross through the origin. So this is what all these values of theta are that we just solved for. And so what that means is that a petal, one petal to be exact, is between, say, negative pi over 2n and positive pi over 2n. So pi over 2n is a valid endpoint, or theta b, for our petal, and negative pi over 2n is a valid beginning angle for our petal, theta a. And so this is going to be the same thing as 1/4 times theta b minus theta a plus 1 over 2n times sine of 2n theta b minus sine of 2n theta a, where we can plug in the correct values of our bounds for this petal. This will be pi over 2n minus negative pi over 2n plus 1 over 2n sine of 2n pi over 2n minus sine of negative 2n pi over 2n. So this looks a little bit complicated, but it's really not that bad. It's going to end up simplifying a lot. You have 2n over 2n, 2n over 2n. And then here we have pi over 2n minus negative pi over 2n is going to be the same thing as 2 pi over 2n, which is just pi over n. And then sine of pi is going to be 0. And sine of negative pi is also going to be 0. So this entire term is just 0. And finally, then we have that the area of the pedal that we're looking for is pi over 4n, which is super cool. This is the exact area of one pedal of the rose for any value of n, right? For any of the values of n that we looked at. Sure enough, if we switch over now to the plot here, we can directly see this. We also see something really nice as well. For this Riemann sum that I'm drawing right here, the errors here look like they're exactly matched because of symmetry here. So the overestimates here are the same as the underestimates here, and we get a really fast convergence here of the sum of each one of these areas. So you can see this is the error right here. The sum of the errors minus pi over 4 times n. And really, I can add and change n here. I will get a different area, pi over 4n, because n will be different. But the idea here is that what we've just done is solve a whole bunch of different problems in general by essentially solving for the rose problem in general, the general solution of it. The area of one pedal will be pi over 4n. And one of the last things that I wanted to touch on quickly in this lecture was what happens if we have maybe a slightly more complicated polar region. This happens from time to time, and it turns out that it's really straightforward to apply this formula a little bit more generally. For instance, let's say I have two polar curves. One polar curve given by we'll call it r is equal to h of theta maybe that polar curve looks going from here or from here to here. And it looks like this maybe. This is r is equal to h of theta. And I have a different polar curve. R is equal to some function w of theta. Sort of an outer polar curve and an inner polar curve. And we'll say this is the angle theta A, and this is the angle theta B. how would we find the area in between these two polar curves? And there's no real trick here. We know that the area bounded by the outer polar curve, w of theta, is equal to the integral from theta a to theta b of w of theta squared over 2 d theta in the area bounded by h of theta is the integral from theta a to theta b of h of theta squared over 2d theta. So the area that we're looking for, A, is going to be A w minus h, or in terms of one integral, the integral from theta a to theta b of w of theta squared minus h of theta squared over 2 d theta. And this is a very useful idea for many problems. So there are a number of really good practice problems in your homework, in the web work. I recommend you going through and trying some of those. But I think this will be all for the lecture today. I hope you learned something, and I hope you had a great day.